As promised, let's do some examples from 3.5. We want to really get the hang of this, so you got a few extra homework assignments this time, but we really want to do a good job with these things and really understand what's going on. Let's look at number 2, where we have y is equal to the square root of 4 plus 3x. Well, hopefully one of the things you want to be able to do is quickly identify the inside function. In this case, I think you'll agree that u, the inside function, is the 4 plus 3x. And then y can be written as the square root of u, which we'll want to write as u to the 1/2 to use the power rule. Now what are we after? We're after dy dx, which again is going to be, how does y change when we change u? How does u change when we change x? Well, dy du is 1/2 u to the negative 1/2 times du dx. Well, it's the derivative of this function, this linear function with respect to x, which is just going to be the slope of 3. So let's rewrite it now. Let's have 1/2 times the quantity. What is u equal to? U is 4 plus 3x to the negative 1/2 all times 3. If you like, you could write this as 3 divided by 2 times the square root of 4 plus 3x. Alright? Now what I want you to start being able to do is not write out the u every time. We want to kind of get better and kind of take some shortcuts here, and that is going to be to say, let's take this quantity to the 1/2 power. And then the derivative of this, let's just call it y prime here. So let me just kind of do the same thing. I'm going to think, all right, I got this inside function, something to the 1/2. So I'm going to bring that 1/2 down, leave what's inside alone to the negative 1/2, and then times the derivative of what's inside, which in this case is 3. Notice that this is the same thing that we got right here. So you want to get good enough where you don't have to write out the u every time. We'll do maybe a couple more with the u, but then we're going to start just doing them with that shorthand notation. Next one we want to look at, how about number, let's see, how about number 12? I'd say 12 is a good one. 12, we have that y is equal to a cubed plus the cosine to the third of x. Now I assume that x is our variable here and a is a constant. They don't say for sure, but we'll assume that we are looking for dy dx. Alright, so dy dx is going to equal, let's go ahead and write out the u again. It's going to be du dx, or dy du rather, times du dx. This time, what are we going to let u be? Well, our inside function u is actually going to be cosine. Let me rewrite this function. Cosine to the third of x, remember that means cosine of x raised to the third power. Okay, so our u is going to be, in this case, cosine of x. That means y then becomes a to the third plus u cubed. Remember, a is just a constant here. The only reason a is in here is to throw you off. It's just a constant, so the derivative of that is going to be 0. It's not going to be 3a squared. A is a constant, so a to the third is a constant. The derivative is 0. So let's go ahead here. dy du, the derivative of this function with respect to u. Again, a is a constant, so it's 0. U is our variable that we're taking the derivative with respect to, so we'll take the power rule there. That's 3u squared. Times du dx. What's the derivative of cosine? I want you to have these memorized. That's a negative sign. Hopefully you did. Had a couple like that on the last test. Replacing the u with what it's equal to, u was cosine x. So we have 3 times the cosine of x squared times a negative sine x. Let's clean this up a little bit. Let's put the negative out front, and let's write cosine of x squared as cosine squared of x. We don't need parentheses there, I guess, but there we have it. All right. So what I want you to be able to do is go directly from this to this. Y prime is, well, the derivative of a cubed, that's a constant, that's 0. Plus, here I got function cosine of x to the third. So I'm going to take 3 times the cosine squared of x, leave that alone, and then times the derivative of what's inside, which is a negative sine x. I'll just put the negative out front and sine x. So that's what I want you to be able to do, is just quickly go from there to there. Let's try another one while we're on a roll here. Yeah, let's go ahead and do 16, I guess. 16. I don't want to do all your homework problems for you. I want to give you guys some practice yourself. But 16 is a good example of using the product rule and also the chain rule at the same time. I'll let you guys do 18 on your own. That's another example similar to a homework problem where you're using the product rule and the chain rule. But 16, here we have y is equal to e to the negative 5x times the cosine of 3x. Now, first of all, we recognize this as a product of two functions. The first one is e to the negative 5x. The second is the cosine of 3x. All right, let's go ahead then and take our derivative. So remember that by the product rule, y prime is equal to, or dy dx is probably the better notation. It's equal to the first times the derivative of the second. Well, let's go ahead and see if we can just do this on the fly. What's the derivative of cosine 3x? Well, here my inside function is 3x. So I'm going to take the derivative of the outside function first and leave the inside function alone. What's the derivative of cosine? Derivative of cosine is negative sine. So that's a negative sine of the same inside function. Now I'm going to take that times the derivative of what's inside. The derivative of what's inside, derivative of 3x, is just 3. So if everybody saw what I did there. First left alone times the derivative of the second. So all of this right here is the derivative of cosine 3x. We have an outside function. If you like, you could say we have u is equal to 3x, and then y, well, y is a bad choice because y is the overall function, but we then have the cosine of u. So we took the derivative of the cosine, which is the negative sine of u, which is 3x, and then times the derivative of what's inside, which was 3. So there's first times derivative of second. Now remember, we're in the middle of the product rule here, so let's add to that second left alone, so that's the cosine of 3x, times the derivative of the first. Well, the derivative of the first is also going to be a chain rule. Here, the inside function is the negative 5x. So I would let u be a negative 5x, and then I would have, well, again, I'm using notation here with y, but y would be e to the u. So when I take the derivative of the first, I'm going to have the derivative of e to the u. Well, that's the same thing. Derivative of e to the u is e to the u. E stands for easy. But my u is negative 5x times the derivative of the inside function. The inside function is that negative 5x, so that's a negative 5. That's on the ground level there. Let's clean it up a little bit. We've got a negative 3 e to the negative 5x sine 3x, and then minus 5 cosine 3x e to the negative 5x. And if you wanted, you could yank an e to the negative 5x out. But that is our solution for that. So again, you're using the product rule, and while you were doing the product rule, you had to do the chain rule. That'll often be the case. You'll have to do more than one rule at the same time. All right, let's see a couple more examples here. Let's see, 22 or 26. Let's do 26, I guess, where we have y is equal to e to the u minus e to the negative u, all that divided by e to the u plus e to the negative u. So the first thing I recognize here is that we have ourselves a quotient rule. We have a quotient, so we're going to do the quotient. Now notice that our independent variable here is u as opposed to x. So what I'm looking for here overall, when it's all said and done, is dy du. So don't be confused by the notation. Here u is playing the role that is usually played by x. Let's use the quotient rule, which says it's the bottom, so low, times the derivative of the top. Alright, let's go through the top here. The derivative of e to the u is just e to the u, minus the derivative of e to the minus u. Well, that's going to be the same thing, e to the minus u, times the derivative of the inside function. The inside function here is a minus u, and the derivative of that is a negative 1. Alright, so that is the derivative of the top. Bottom times the derivative of the top, minus the top, which is e to the u minus e to the negative u, times the derivative of the bottom. Let's do the derivative of the bottom here. E to the u, that's just e to the u, plus e to the negative u. Well, that's going to be the same thing times the derivative of the exponent. Derivative of negative u with respect to u is that coefficient of 1, negative 1 rather. So there it is, all of that divided by the bottom squared. Low d high minus high d low, all above the square below. Let's clean it up a little bit. So we got e to the u plus e to the negative u times the quantity of e to the u. Here's a negative 1 times a negative makes that a positive e to the negative u, minus e to the u minus e to the negative u times the quantity of e to the u minus e to the negative u. All of that over the bottom squared. Alright? So don't let these e's fool you. They're still just as easy as they always were. I mean, if y is e to the 5x, all you have to do is rewrite. If you have e to a power, you just rewrite it and then multiply that times the derivative of the exponent. What's the derivative of 5x? It's 5. Alright? If you've got y prime equals e to the x squared, alright, you got an inside function of x squared. I'm sorry, this is just y equals that. This is a different problem. Well then, y prime. E to a power, you just rewrite it and then multiply by the derivative of the exponent. The derivative of x squared is 2x. So you have 2x e to the x squared. All right. So it isn't that hard. It just takes a little bit of practice. Okay, and I think we have time for one more. And this one, I mean, if you guys aren't used to problems like this by now, you may never be used to them. Find the equation of the line tangent to the function y equals the sine of x plus the sine squared of x at the point 0, 0. So again, the equation of the line tangent to this curve at the point 0, 0. All right, here we go. You guys know what to do. First thing we need to do is find the derivative. So we need to find dy dx. And dy dx is going to be equal to, let's see, the derivative of sine of x is cosine of x. Now the derivative of sine squared of x, remember that's the same as the sine of x quantity squared. So my inside function is sine of x. My outside function is a quantity squared. So I'm going to do the derivative of my outside function first. Something squared, that's 2 times that thing raised to the first power, and then times the derivative of the inside function. The derivative of the sine is the cosine. Okay? So what do we got? We've got the cosine of x. That was the derivative from the first function, sine of x. And then we move to the second function. We have the sine squared of x. Again, you can think of that with a u being sine x and the y being u squared. So it's 2u times the derivative of sine, which is cosine, u being, again, the sine. So what do we get here? We get plus 2 sine x cosine x. So the 2 comes down in front, reduce the power by 1, and then multiply by the derivative of the inside function. The derivative of sine is cosine. I think you guys got it. Now we want dy dx. This gives us the slope of the line tangent at any point on a curve. In particular, we're interested at the point where x is equal to 0, since that's the 0 value is what's given to us here for x. All right, so what do we have then? We're going to have the cosine of 0 plus 2 times the sine of 0 times the cosine of 0. Now the cosine of 0, everybody, that's right, 1, plus 2 times the sine of 0, that's right, 0, times the cosine of 0, which is 1, so it all comes out to be 1. Remember, this is the slope of the line tangent. Don't forget what the derivative tells you just because we got some fancy shortcuts now. Always remember exactly what the derivative means. It means the slope of the line tangent to the curve, how fast the function is changing at any particular point in time. The velocity, the instantaneous rate of change of your function. All right, so what do we have then? We have, basically, if we remember what we're doing here, we have a line with a slope of 1. We found that by taking the derivative and plugging in our x point that goes through the point 0, 0. Well, that's just y equals x, right? Y equals 1x plus 0, y equals x, and as usual, let's go ahead and graph it. So using our favorite graphing program, WinPlot, W-I-N-P-L-O-T, and that's free. I encourage you to get this software. It's very good software. I put in the sine of x plus the sine squared of x. So I put it as the sine of x, that quantity, squared. Now let's go ahead and put in our line and see if it's tangent. Notice that it does go through the point 0, 0, and it looks like we're going to be in business, like y equals x is going to be tangent to it. Let's graph it. Y equals, sorry about that, pay no attention to that, y equals x. There it is. Sure enough, it is tangent to the graph at that point. That is some good stuff right there. All right, let's get a password for you. And to get into your 3.5 homework, you're going to type in the word nettle, N-E-T-T-L-E, and that, of course, means to arouse sharp anger. You know, when you're bugging someone until they just snap at you, you're nettling them. I don't know. N-E-T-T-L-E, that's your password. Good luck. Due Wednesday. Let me know if you have any questions.